So now that we've kind of looked into the properties of limits, it's about time we actually start looking at the definition of continuity in terms of a limit. Again, you're going to see many definitions, in real analysis about continuity. However, in Calculus 1, this definition over here will suffice. So suppose we have a function f of x, and this function f is said to be continuous over all real numbers, so continuous over r, if and only if, for all a values, the limit as x approaches a from values less than a is equal to the limit as x approaches a from values greater than a, of course, of f of x, and that also has to be equal to f of a, and of course it has to exist. So essentially, it can't be equal to infinity. Of course, if you're assuming that a is not equal to infinity, then this has to be some existing finite value. They have to be equal to each other, and it has to be the function evaluated at a. Also, I don't know why that's an x. That should be an a right over there. Now, if this holds true, then we can just take, whenever we're evaluating limits given the actual equation of the function, then we can just use what we call direct substitution. So direct substitution, which is essentially what we've been doing, where we just take in the value of a. We just take a and put it into the function, and then that gives us the limit, because the function is what we say continuous. So a good kind of, if you want to look back at, pre-calculus, we define continuity as kind of if we have to pick up our pencil while tracing the graph. So right over here I have a good example of a function that's not continuous, y equals 1 over x. We know it's not continuous because we have an asymptote right over here, right down the center. I'm going to trace that. Is it going to trace? Okay. And this asymptote is going to have the equation x equals 0. Now, how can we actually determine that there is going to be that asymptote over there using limits? So let's go ahead and actually test this out. So suppose we wanted to take the limit as x approaches 0 of 1 over x. Now, how do we know that there's going to be a vertical asymptote over here? Now, we could try this method of direct substitution. We can just say, okay, supposing that 1 over x is continuous, then we can say this is just going to be equal to, 1 over, where you just replace x with whatever value of a is, which would be 1 over 0. And then we kind of have a little bit of an issue, right? Because we're dividing a number by 0, right? So that doesn't necessarily work out, so we can't necessarily say that this is true. So then what we can do is we can say, okay, let's just kind of think about this in terms of approaching 0, so values that are approaching 0. So let's consider, like, I don't know, perhaps we can try this value over here. It's just barely above 0. Maybe this is like 0.00001. And then we can input that into the function, and then we're going to get some very large number. I don't know, it's going to be like, what is this going to be? Like 100,000? I don't know. And then we can try, from values that are less than 0, we can say like negative 0.0001, for example. Take 1 over that, then we're going to get a very negative number. So it's going to go to negative infinity. And then essentially what we're doing is, as the values get closer and closer to 0, we're going to be approaching positive and negative infinity. So we can say the limit as x approaches 0 from values that are less than 0 of 1 over x is going to be negative infinity, right? And so we can see that over here from the graph. As we approach 0 from values that are less than 0, from negative values essentially, then our function kind of just asymptotes towards negative infinity. It gets smaller and smaller as x approaches 0 from the negative numbers. And then if we want to consider the other limit, the other one-sided limit, we take the limit as x approaches 0 from values greater than 0 of 1 over x, then this one we can already tell is just going to be equal to positive infinity, right? And we can determine that by, kind of approximating it by getting closer and closer to 0 from values that are greater than 0, so from the positive numbers. And we can tell, for example, with this number over here, our function 1 over x is just going to keep getting infinitely large. It's going to asymptote towards infinity as x approaches 0. So right away, just from this one particular example, we can immediately say that 1 over x is discontinuous by this limit definition over here. Because, first of all, these two limits are not equal to each other, right? These are not equal to each other, and also they're infinite, so they, it's not necessarily a real number. Infinity is not technically a real number. And And so essentially we can say that 1 over x is not continuous or discontinuous. And I mean, you can determine this graphically, but if you're asked to kind of prove, you can come up with a counterexample to prove that a function is not continuous if you aren't really given it graphically. And in general, if you want to determine whether or not there is a vertical asymptote at a particular point, so we can say in general, if you have a particular value a, for example, and we take the limit as x approaches a of f of x, and if this yields something like k over 0, where k is not equal to 0, then we can say there is going to be a a vertical asymptote. I'm just going to denote that VA at x equals a. So this is just kind of a general case over here. There's going to be a vertical asymptote at x equals a if when you're taking the limit, you get some non-zero value divided by 0. And I mean, I know we just took one particular example, but you can test this out for various functions that have vertical asymptotes at particular points, and you'll see that it actually does, in general, hold true. And then we're going to look at the other discontinuity, or the other kind of crucial discontinuity that you can determine kind of graphically, or actually no, given the equation of a function. And that's what we call a point discontinuity, or a removable discontinuity. And then, so let's take this example over here, y equals sine of x over x. And essentially, if we take the limit, I don't know why that's glitching. If we take the limit as x approaches 0 of sine of x over x, then we can again try direct substitution, and then we're just going to get sine of 0 divided by 0, right? Which, I mean, there's already a problem here. We're dividing by 0, but then, moreover, sine of 0 is going to be equal to 0. So we have 0 divided by 0, which is what we call an indeterminate form. We're going to actually learn later on how, under certain conditions, we can actually kind of figure out a way to potentially determine a limit when we're given this indeterminate form of 0 over 0. But as of right now, we can say that the limit doesn't exist, and we can say that there's going to be a point discontinuity, or a removable discontinuity. And I mean, if we want to look at it graphically, this is kind of just a sketched graph of sine of x over x. We can see as we approach 0 from both directions, we're approaching some value over here. I mean, it looks like we are approaching a value, but we do have a point discontinuity, and that's why we can't actually use direct substitution. Again, we can approximate this thing. We can say, we can start taking values that get closer and closer, that approach x equals 0, and we can input that into our function over here, and you will actually, this just so happens to be equal to 1. But so this point right over here where we have the discontinuity is the point 0, 1 is where we have a discontinuity. So we can actually get a limit, like we will have a limit, but we can't use direct substitution in this case to determine it. Again, later on we will start looking into ways to determine it when we get this indeterminate form. But in general, again, we're just making some generalities over here. If we have the limit as x approaches a of f of x, and by direct substitution we get 0 over 0, then we'll have what we call removable discontinuity, or point discontinuity. So removable discontinuity. And I mean, these ones are, you can evaluate them graphically. Maybe you can kind of just like inspect this limit and say, although we can't determine it from the equation of the function, we can actually determine it graphically in this particular case, or in many different cases you can find. So these are the two kind of general ways to determine discontinuities from a limit. In general, if you have some non-zero value divided by 0 after you kind of use direct substitution, then we can say that there's going to be a vertical asymptote at x equals a, as we saw in this particular case over here. And in general, if you use direct substitution to evaluate a limit and you end up with this indeterminate form of 0 over 0, then you can say that you have a removable or a point discontinuity at x equals a.